You'll notice when you're going through the lecture videos that there's a lot of examples and problems that we do and we work out in the videos. And when you're looking at those, a lot of them have these little icons like these things, and they sometimes just appear and disappear at different points in the video. And I wanted to go over what these mean because these are things that I talk about in my class, but you may not know that if you're not in my class. So here's a little summary, and we'll do this in terms of an actual problem. And this image is called "Don't Panic" because I always call these are the steps to do the problem. So step 0, don't panic. Step 1, draw a picture. And this is sort of a side step because a lot of the time the problem's already given, but if you're doing homework, it's nice to sometimes either summarize the problem or at least make sure you've read through it. So it's sort of an in-between step, like a step 1/2, okay? Because step 1 is always draw a picture. So we're going to go through with an actual problem, and I've written one out. So we're going to zoom in on this a little bit. So when we're writing or summarizing the question, we want to know if a ball is dropped from the top of a 100-meter high building, how fast is it going when it hits the ground? Okay? So you want to look for indicators when we're going through this of what sort of things you should be looking for in the problem. So even if you don't have to rewrite the problem, you want to look for keywords and numbers, okay? So first off, if a ball is dropped, that sort of implies free fall, okay? So this is probably a free fall problem. We're given a distance and also another point of distance, okay? So we have 100 meters, that's the height of the building. We have the ground, that's probably 0, although we don't have to call it 0. And then the last thing is what we're asking for. How fast is it going? So that's probably our final speed. Now implied in this, in dropped, is our initial speed. That means it's not thrown, so it probably starts with a speed of 0. Okay? So that's our problem. The next thing we're going to do is we're going to draw a picture. So let's go with our draw a picture. And I'm going to put this down here. So draw a picture. Now it's not just drawing a picture because obviously we can draw this building. So here's our building. There's the ground down here. There's somebody up here. And they're dropping a ball. This is not to scale. They have terribly long arms. Okay? So we'll just draw the ball. We don't need the person. So here's the ball. Okay? Now, whenever we draw a picture, it's not enough to just draw the picture. We have to label it, and we also want to usually pick a coordinate system of some kind. So here's our coordinate system. Here's X, here's Y. We're really going to only use Y, but hey, it's good to have extra stuff. So this Y in meters, this is 100 meters, and this is 0 meters. Okay? As for the speeds, we know up here, V initial should be 0 meters per second, and down here, V final is what we're looking for. So as this guy falls, okay. Now there's a couple different ways to solve from here, but this is all we really need for our picture. So the important thing here on the picture is we have these labels, a coordinate system, and we've included all of the values and variables that we thought we might need. So the next thing we're going to do is list the knowns and unknowns, and we've already kind of done that. You don't always have to do this in order. But it's a good reminder when you're doing this of what to do next. So what are our knowns and unknowns? Well, let's do it more formally because we have it on the picture, but we know Y initial is 100 meters. Y final is 0 meters. V initial in the Y direction, which we don't need to write because we don't have an X direction, but sometimes it's good practice, is 0 meters per second. And then V final in the Y direction, we don't know. That's our unknown. The other thing we might want to remember is acceleration in the Y direction. That's going to be negative g. I don't think anything else is necessary. That's all of our knowns and unknowns just from reading the problem. Then we want to write the equations. Now, There's actually two different ways to solve this problem. So the equations you use, it depends on how you want to do it. So when we write the equations, we can use either conservation of energy, which means that we're going to use K initial plus U initial is equal to K final plus U final. Okay? Then we see that initially energy, and at the end we only have kinetic energy. So this would be mgy is equal to initial is equal to 1/2 mv final squared. Okay? So that would be the equations you would use if you're going to solve it with energy. You can also solve it with kinematics, in which case you would need one of your kinematics equations just in one dimension. Next, we want to make an estimate. And this is something a lot of people skip, but it's pretty important so that you know about what to expect from your answer. So let's make an estimate. What do you think a reasonable speed is when you fall off a 100-meter building? First off, what's that in feet, for instance? And we can always ask Siri. Siri, what's 100 meters in feet?
It's 328.08 feet.
This is 328.08 feet. So you're basically falling a football field, right? We know we often want to change units so we have something more intuitive. So do you think it would be reasonable to say that you're going pretty fast by the time you fall an entire football field? We start with pretty fast, but we usually really want an order of magnitude estimate, and that just means like some factor of 10. So do we think 10 meters per second is reasonable? What about 100 meters per second? What about 1,000 meters per second? I'm going to guess it's somewhere between 10 to 100 meters per second. Okay, that's our estimate. That's what we think would be reasonable for falling off a building. Sometimes you might want to do this by doing some quick calculations, but in this case we could probably just use intuition. All right, so we made our estimate. We think it's somewhere between 10 and 100 meters per second. We're going to solve symbolically now. So we're going to take what we already did from up here, and we're going to solve it for, what are we solving for? Well, we want to know how fast this thing's going, and we're looking for V final. So V final. So we're going to bring this down here and solve symbolically. So that's mgy naught 1/2 mv final squared. So we can see the m's are going to cancel. That means we have V final is equal to 2gy naught square root. So we've solved symbolically. Now we move on to the next thing where we can plug in numbers. So once we plug in numbers and we plug this into our calculator, we get 2 times 9.8 meters per second squared. It's important to make sure you include the units. And then y, which is 100 meters. All right, so we're going to plug this into our calculator. And look, before you get really dependent on the calculator, this is really 2 times 10 times 100. Okay, so the square root of about 2,000. You can kind of guess what the square root of 2,000 is, and we get something like 44.3 meters per second. And this is our V final. And so now we have our answer. Now one thing we want to ask ourselves, looking back at this, does this match what we guessed? Does it make sense? Does it match our estimate? Does it have correct units? Does the algebra look good? So we do have correct units, right? We know velocity is in meters per second. Does it match our estimate? Well, yeah, 44 meters per second is between 10 and 100 meters per second, so that makes sense. The algebra looks good, so this answer checks out. And this is how we go about problems, right? If we go through these steps, not only are we going to get an answer, we're going to have an idea if this answer is correct. So when you're looking through these problems, I'm going to try to follow this procedure every time so you get used to doing that when you're doing problems on your own. Thanks for watching.